Welcome back to another topic on General Chemistry 2, Colligative Properties of Electrolytes Solution. Before we proceed with our lesson, let's have a brief review of what we had tackled previously. We learned the expressions of concentrations and the colligative properties of solutions. For expression of concentration, we have percentage composition. This includes your percent by mass, percent by volume, mole fraction, and percent weight by volume. We also tackled special or commonly used expressions of concentration. We have your parts per million, parts per billion, and proof. We have molarity, molality, and normality. For colligative properties of solutions or colligative properties of non-electrolytes, we had your vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So will the colligative properties of electrolytes be different from the properties of non-electrolytes? I'm giving you 30 seconds to think about this question. Well, to answer that question, we will have to look into our current lessons. Here, we will differentiate the colligative property of non-electrolyte solutions and of electrolyte solution. We will calculate boiling point elevation and freezing point depression from the concentration of a solute in a solution. We will calculate molar mass from the colligative property data, and we will describe laboratory procedures in determining concentration of solution. So let's compare non-electrolyte versus electrolyte solutions. Non-electrolytes do not create conductive solutions, whereas your electrolytes are substances that are once dissolved in water will start conducting electricity. Particles of non-electrolytes do not dissociate into ions, whereas our electrolytes would dissociate. Here we will compare the colligative properties of non-electrolytes and electrolytes. Well, they both have colligative properties. If electrolytes have vapor pressure lowering, non-electrolytes will also have vapor pressure lowering. As for boiling point elevation, both of them do have boiling point elevation, as well as our freezing point depression. And finally, do you think both have osmotic pressure? Of course, they both have osmotic pressure. But what makes them different? Well, because electrolytes dissociate into ions, we have to factor the Van Hoff factor. Whereas for non-electrolytes, we don't have a Van Hoff factor. But what is a Van Hoff factor? Van Hoff factor I accounts the dissociation of ions in a solution. Let's calculate Van Hoff factors of the following compounds. First, let's have HCl. We know that when we dissociate HCl, or if HCl would undergo decomposition reaction, it will form two ions, which is hydrogen ion plus your chlorine ion. Let's do a bit of balancing. H on your reactant side is 1, and H on your product side is 1. And this is the same with our chlorine. Therefore, the Van Hoff factor I of HCl is 2. Next, we have your NaCl. If NaCl dissociates, it will form Na positive plus your chlorine ion. You have two ions here, therefore the Van Hoff factor is 2. How about magnesium sulfate? It's MgSO4. If it dissociates, we will have your magnesium and your sulfate ion. Therefore, our I is again once more 2. How about magnesium chloride? If magnesium chloride dissociates, it will form your magnesium ion plus your chlorine ion. Let's balance it out. If you have one magnesium in your reactant, you also have one magnesium in your product. How about our chlorine? We have two chlorines on the product side, therefore we have to make sure that there are also two chlorines on our product side. Therefore, the Van Hoff factor is 2 plus 1, 3. And finally, our last example is FeCl3. We'll have our iron plus our chlorine. And if we balance this equation, we will have the coefficient of iron as 1 and chlorine as 3. Therefore, our Van Hoff factor is 3 plus 1, which is 4. Did you get that? Okay. How about if we are calculating the Van Hoff factors of weak electrolytes? For this one, we will use this equation. I is equal to the actual numbers of particles in a solution after dissociation over the number of formula units initially dissolved in a solution. In a sense, this is just I is equal to equilibrium divided by initial. Or we can also use this equation using our degree of dissociation, wherein alpha is our degree of dissociation, I is our Van Hoff factor, and N is the maximum number of ions formed per molecule of the weak electrolyte. So how will we go about this? Well, I believe we will have to review our lecture on basic stoichiometry. See you in the next video on basic stoichiometry.